Eric Muller from Imperial College, and over to you, Eric.
Well, thank you. I'm going to change a little bit the tone. I'll talk a little bit about coarse graining, actually modeling, molecular modeling, and MD modeling of liquid crystals. And but more importantly, I'm going to talk a little bit about how to pass between our common coarse graining models and more large-scale engineering models, and how to bridge these scales. So first I'll talk a little bit about coarse-grained modeling just to set the scene. I'll talk a little bit, then I'll change gears and talk a little bit about the equation of state and SAFT and more engineering models. And then we're going to put them together and you'll see how things start shaping up little by little. So the first thing I'm going to talk is about just generic coarse graining. And the first question is what is coarse graining and why would you want to do coarse graining? So as an example, I place here a bola amphiphil, which is a liquid crystal which has quite conflicting views on its own nature. It has a very rigid central core, but it's decorated on both sides by polar groups which form hydrogen bonds and which are very philic to each other, but are not philic to the rest of the molecule. And on the side of this molecule, you have a fluorinated chain, or you can have different types of alkyl chains, which again are not philic to each other, three parts of the molecule. So it's a rather interesting molecule. There's actually a poster outside from the Patras group, which also deals with these types of molecules, which are very schizophrenic because the molecule doesn't like each other. But it's very nice because it forms very beautiful liquid crystal faces. This molecule particularly was synthesized by the group of Carson Sherkin. But what I want to talk is if you want to do a fully atomistic modeling of this, an MD atomistic modeling of this, you really have to do a heroic job. Tomorrow there's I think some talks about some of these heroic simulations, massive simulations. You would want to have about 100 atoms. You have about 100 atoms. You want about 1,000 molecules in your system. You're talking about roughly 10,000 million calculations for each simulation step. So these are enormous numbers, even for today's standards. So the idea, of course, is to decrease the computational effort. I might say that the computational effort has become larger and larger with increasing time. Today's iPhone has as much computing power as the largest Los Alamos supercomputer of 40 or 50 years ago. So we have advanced enormously. Between November and today, new GPU cards have appeared, which at least in our simulations have speeded it up by 1 order of magnitude. And this is just in a few months' time. But in spite of this enormous computing power, there's still the need to now explore other things. So how would we go about doing a simpler version of this? Well, our view of this is to take the parts of the molecule and convert them into some sort of superatoms, which each superatom takes part or corresponds to a group of atoms of a similar type. Notice that one thing I'd like to stress is notice that I've used spheres to model the parts of my molecule. This has one particular advantage. I mean, there has been a little bit of talk about the Gay-Byrne model and the virtues of Gay-Byrne model. And yesterday, one of the things that was discussed in the history of the Gay-Byrne model was that was omitted actually from the talk was that Gay and Byrne actually thought first of using 7 Lennard-Jones spheres put together, and then they recognized, well, look, this is computationally too difficult. Let's have a better model, a simpler model, which has just one side. But the underlying Gay-Byrne model is actually made of spheres, which at that point was probably a little bit too much. Maybe now it's not so much. Now, skipping that, if we form a coarse-grained model in this type, in which the colors, of course, represent the different types of philic sites, so the red would be the very hydrophilic sites. These white beads would correspond to the benzenic type moieties in the center, and these would correspond to the fluorinated models. We will increase our simulation speed by actually 1 million times. That's 6 orders of magnitude, which is quite good. Now, why do we want to increase the speed so much? Well, there is a reason for that. And the title of this slide kind of sounds stupid. It says self-assembly requires time. But what type of time does it mean? So now let's take this simple bowl amphifill and let's put it in an isotropic state at high temperature and then suddenly quench it. And we're going to do this by MD. And what we'll see here here is a columnar order parameter which describes basically what is happening in the system. And what we have here is time. I might mention that it is in nanoseconds. And you see that we really have to explore very large times in order to actually see the correct self-assembly and the event that triggers the formation of this very nice columnar phase, which is characteristic of these types of bowl amphiphils. Notice that if you were going to do an atomistic simulation, it would probably span around 5 nanoseconds. So you'd span something around here, and you actually missed out on the nice events. So that's what I mean by time. We need to look at really large times, but not unreachable times. I'd like to show you another example of what I mean by looking at large timescales and time frames. This is another type of molecule by the group of Persek. This is again a very paranoid molecule, polyphilic molecule, which has a polar group at the apex of a more or less triangular molecule, a reasonably rigid intermediate section which is formed by benzenes, and a long tail. These are 11 alkane chains, which are alkyl-like. So again, we have 3 parts of the molecule, and the 3 parts don't like each other. Now, the interesting thing is that some of the people that have worked experimentally with these systems recognize that for the very smaller types of dendritic of these dendritic liquid crystals, they form something that looks like they see like a little pizza wedge, and these pizza wedges self-assemble into a columnar structure. But if you have a larger type molecule of the same style, but just another generation of the same molecule, these look like little cones, and the little cones self-assemble into what apparently looks like a sphere. So again, our coarse-grained model, of course, has to lose a little bit of that molecular detail, but doesn't lose completely neither the morphology, neither the energetics. So we have a self-attractive head, a reasonably self-attractive, but different type of this is the benzene types, and we have the little alkanes, the alkane tails. And what we proposed to do was to try to derive the global phase diagram of this system by changing pressure and temperature. And just jumping the gun, we recognized that for that same configuration, we would get all the experimentally observed mesophases, regardless of the size. So it wasn't only just size, and pressure and temperature regions were also very important. So at the start, we have at high temperatures, we have an isotropic phase characterized, of course, by basically nothing. You just simply see that the system just is completely isotropic. The moment you start lowering the temperature, you start seeing that now the molecules have formed little clusters, and these clusters resemble that sphere I showed you. And if you follow the spheres in their movement, they look very much like a liquid. So we're talking not only about a liquid crystal in the sense that these molecules go from one of the spheres to the other, but we're also talking about for a liquid from a supramolecular point of view. If you keep lowering the temperature, very interestingly enough, these spherical moieties start assembling into now have spatial structure. And now again, we still have a diffusion between the little spheres, but we now have a spatial ordering of these spheres. Keep increasing keep lowering the temperature or increasing the pressure, and what you see is that these spheres now coalesce into a columnar phase, which is again reminiscent of what the pizza wedge model showed. So we see that we can see all of these all of these phases without without the need of any artificial description on effects of sizes and things like that. So as I promised, I'm going to change gears then now. I mean, this is molecular modeling, and this is what we like to do with the liquid crystals. I'm going to talk a little bit about what the engineers do on this type of problem. This is basically the equation of state modeling. And the particular equation of state I'm going to talk about is the SAFT equation of state. SAFT represents the statistical associating fluid theory, and it's basically a perturbation approach which that helps us describe the behavior of simple fluids and chain fluids. The word associating comes from the fact that we're talking about linking, decorating our spheres with sites that resemble hydrogen bonding sites. And the theory allows us to play with the strength of these hydrogen bonding sites, even taking it to the limit of an extremely strong bonding site. So if you have spheres with extremely large hydrogen bonding sites, eventually they'll form chains. And once you have that, you have a description for an equation of state of a fluid made of chains. So now you're starting to understand why I decided to choose to build my molecules just with spheres and with little chains, because then I might be able to use macroscopic equations of state to try to describe them. And usually at this point, I apologize for the appearance of equations in my talks. Now I have to do just the opposite. I have to apologize for not putting enough equations. So I'm always apologizing. Basically, the SAFT equation of state is a perturbation approach. We express the free energy, or the Helmholtz free energy, as a term of course, an ideal term, a term that corresponds to a monomer, or basically a sphere, an isotropic sphere, and itself, that monomer can itself be expressed in a perturbation term in terms of a hard sphere and the elements needed to add attractions to it. And I'll talk a little bit about the attractions. Basically, our version of SAFT corresponds to a me potential. So it's an extended Leonard-Jonesian type of potential. In the version I'm going to talk today, we also have the chain term. And the chain term is also an added perturbation to the scheme, which takes into account the number of bonds, basically the number of bonds made between these spheres to describe a chain. You could add, and there are different versions of SAFT, the original version of SAFT will have an associating term here, which is not relevant to us. And you could even add other terms corresponding to this. There's basically 20 years of SAFT development, and there's many flavors of it. So you'll probably see different, or have heard some versions of it before. The one we used here is one in which we look at the me potential. And the me potential is an expanded version of the Leonard-Jones potential, where the exponents are free to wander to different values. And this gives us a very interesting and powerful tool to fit the Leonard-Jones potential, or this Leonard-Jonesian potential, this Leonard-Jonesian chain term, to actually real substances with a high degree of accuracy. In most cases, this exponent is fixed to 6, and basically we have then just 3 parameters, which are the characteristic size, the well depth, and basically the steepness of the potential through an exponent. The engineering-wise, this equation of state can be used to fit simple molecules and even more complex ones. Here are some examples of small phase diagrams for simple mixtures. The solid lines correspond to the SAFT. You can use the experimental data to find these parameters which are missing. Probably the power of the equation of state versus more simpler van der Waalsien types of equations of state is that it can be expressed in a group contribution form. Each of these spheres can be, for example, in a polyethylene molecule, each one of these groups or spheres can correspond to, for example, a CH2 group. And once you fit the parameters for a CH2 group for a small group of molecules, you can extend them to larger systems. For example, here we have the example of what would happen with pentane and polyethylene. Basically, it's the same CH2 groups, but in 2 different conformations. One is an extremely long chain, and the other one is a very small molecule, all made of the same spheres. And what you can see is that the equation of state is giving the correct behavior, not only of vapor-liquid equilibrium, but liquid-liquid equilibrium, even up to the limit of the polymer systems. Okay, so that's engineering. That's it for engineering. It's over. And now let's put it all together. Okay, how can we put this all together? Well, our idea is to our basic motive and motivation of the talk actually is to walk up this ladder. Usually for liquid crystals, this is a region of time scales and length scales which are very important. The atomistic scale is of course well defined, but it limits the amount of the length of the simulations we want, and also the sizes of the simulations we want. And the regions of DFT and ab initio simulations are probably not of too much interest. And at this case, in any case, the ladder is broken, and the path from DFT to atomistic modeling is not clear, is not unique. No one agrees with this. But it's even worse when we're at the level where we are, because there's no way to keep going up. Okay, the ladder is even further broken, and it's very difficult to jump up. And actually, the motive of the talk is to try to explore ways of jumping, and jumping and reaching that other scale. So by now, I hope you've probably seen how the pieces fit together. Basically, we have an analytical equation of state. This analytical equation of state, and the simple engineering way of using it is to look at experimental data and fit the parameters of that equation of state to the experimental data. And once you have that, you take your equation of state and simply run it many times to obtain the properties of bulk fluids. And if your equation of state is good, your properties represent the experimental data. The twist we want to give to this is that when you did this, you actually found parameters for intermolecular potentials. So you could, of course, use those intermolecular potentials in a molecular simulation. And you could, of course, go back and produce the properties of bulk fluids, and that would be the least interesting thing, because you can already do that analytically with the equation of state. The more interesting thing is that now we can find interfacial properties, you can find transport properties, you can find self-assembly, mesophases, et cetera, et cetera. So let me prove that to you with a very simple example, CO2. There's very simple questions about what is CO2. Again, probably not relevant, but gives a point to exactly to the procedure and the way we work. So we take CO2, and instead of modeling it atomistically as 3 sites and 3 electrostatic charges and everything that, we just say, well, let's assume, and we can coarse-grain it to a single sphere. And let's fit the properties of that sphere, for example, the epsilon, the sigma, and the potential exponents, to experimental data. So what experimental data is available for CO2? Well, a lot of it, but let's choose some of it. For example, liquid phase densities and vapor pressures. You can see in this graph that that we're not experimentalists, because we put the experimental data as little dashed lines here. Okay. So the dashed lines are the only reality, okay? And, well, everything that's not in red are the fully atomistic models. For example, this is, for example, the EPM2 model and several other models which are in the standard fully atomistic, very detailed models. The red is SAFT. The solid line is the theory, so that's a theory we fit. And the symbols are our Monte Carlo simulations for that particular potential set of parameters. You can see, well, there's a little bit of discrepancy at the critical point, but here in the region of the saturated liquid, we do a very good job. Here in the region of the vapor pressure, we do a very good job with the same set of simple parameters. Okay, so now the proof of the pudding, of course, comes with the extrapolation. This is, once we do that fitting, let's see what we do with other things. Again, here we have the dashed lines again as the experiments. The solid line is the prediction from the equation of state, and the circles are simulations. Now, all of these graphs are extrapolations. They're predictions, and they're predictions of different types of thermodynamic properties, high pressure, isotherms. We have Joule-Thomson coefficients, speed of sound, and the different types of compressibilities. So the model is basically Basically, what we're trying to do is take a little bit of information about thermophysical properties, and with a suitable model, obtain a good averaged free energy model. And once we have that good average free energy model, of course, since it's been fit to a wide range of pressures and temperatures, it gives a very good approximate value for our parameters. So we can use them with confidence. And we can use them in confidence for things that we can't use the equation of state for. For example, we can use it for the interfacial tensions. This is an example in which you can see CO2, or again a red sphere, and this is a model. This is our model for alkane, for a C10, an alkane, three beads together. Each of these beads would correspond to a group of CH2 molecules. In this graph, you see the phase separation, but more interesting is you can see the excess adsorption at the interface, and you can see the excess adsorption of CO2 at the interface, something we see from the simulations, and we verify that the atomistic models actually give us the same thing. We can go and now pester our experimentalist friends. This is something that apparently would be very simple: the interfacial tension of CO2 and water as a function of pressure. You would think that in today's world this is something that everyone already knows and has measured. And well, this is what happens. This is the available experimental data, and you can see that around this region there's nothing not even close to an agreement. And in fact, there's quite strange behavior here. When we did our simulation, we looked at this, and there was quite strange behavior. And it happens that in this region there's a three-phase region. In between the high pressure CO2, the liquid water, there's an appearance of a CO2 liquid phase. This is predicted by the equation of state. We do the simulations, we actually see that this is happening, and the experiments, of course, don't see that because experiments are designed to look only at the two phases. The best experimental data we've seen, or we've talked to the person that did this, and actually he confirmed that that's exactly the case. I mean, he couldn't get a good data point. He had to put something there, but that's a reason why these things happen. In terms of speed up, again, enormous amounts of speed up. As I mentioned, this is an older slide. Today's slide is one order of magnitude better than the one a few months ago. In this slide, you have the time per time step and the number of molecules, and the coarse-grained model and the fully atomistic model are separated by several orders of magnitude. If we're talking about, if you're happy with the time you spend in your simulation, you can jump two orders of magnitude in the number of molecules you want, or if you're happy with the number of molecules, you can decrease by 3 orders of magnitude the simulation time, which allows us to do more interesting things, span realistic times, microseconds, for example. I know for an experimentalist, microsecond is nothing, but for a simulator, a microsecond is something very, very interesting. This is orders of magnitude above the types of things that you can see. So here we can see, for example, nucleation of CO2, and actually the effect of interfacial tension with the size of the nanodroplet, something that you can't that you couldn't find out without doing very large simulations. How do we take this into the world of liquid crystals? Well, a way to do that is to exploit the coarse graining, both the coarse graining and the group contribution idea behind this. An example here is non-ionic. The example I'm showing here is non-ionic surfactants. These are very simple alkyl polyoxyethylene type molecules. There are amphiphils in which one part of the chain is the alkyl chain and the other is the etoxy chain. And in a solution of water, they basically form a very rich and beautiful phase diagrams of allotropic phase diagram. Which has several lamellar phases, some isotropic phases with the formation of micelles, etc., etc. So how would we envision this molecule? Well, the idea again is to break the molecule down into groups. These in my computer are shown gray, so they disappeared here, but we have little beads here of different grayish colors. And the idea is basically to take these spheres and parametrize them. But the point is that we're not going to parameterize the whole molecule. We're going to take these and recognize that these are alkane chains and fit them using just the properties of alkanes, which are small molecules which we know very well. And once we have them, we just simply describe them as such. So for example, we can take the properties of the linear alkanes, which there's no surprise to them, fit them accordingly to certain number of beads, and fit the phase equilibrium, again, the liquid densities and the vapor pressures, and get a set of parameters which are roughly, you can see there's roughly certain consistency among them. Whereas it depends on the eye of the beholder how much you want to coarse grain and how much you really believe in the things that we're doing. But you can see that there, across the whole family, there is a generally good agreement on the size and on the energy parameters that a sphere of these alkane molecules would look like. We have here the errors in density, the errors in vapor pressures and heat capacities and critical points, and again, they're all very sensible. So we can do that with the alkane part. We can do that with the epoxy part, for example. We can do exactly the same story. You see that there is some sort of repetition in the terms in the numbers, and not a absolutely perfect agreement, but of course there is a sensible agreement, and we can keep going and going on. The good thing that we do this only once, and once we have that, we end up with a table of parameters for the different parts of the molecule. You have to do the exercise again for many other things. For example, you have to do the exercise for water, and for water you would again have to do some sort of coarse graining. In our case, we've been looking now at coarse graining water, for example, with 2 water beads being a single bead, and that's our water molecule. We also have to find now the interactions. I mean, how does this one interact with this one? How does this one interact with the N group, which is the OH type group? And again, we can do that by looking at smaller molecules. There are smaller molecules which have either a combination of these groups or we have VLE or mixture VLE. So it depends on each one of these ticks. We sometimes look at different things, like, for example, excess volumes or solubilities or different thermodynamic properties of the simple molecules, which are usually available. And of course, what we want to do is to try to see if we can get some sort of correct behavior in a predictive way. Okay, so now we're not looking at fitting a phase diagram. We're just looking at trying to see what it predicts. And in fact, in the dilute regime, we actually see the prediction of the formation of micelles, exactly as we had expected. And in the dense phase, we see the formation of nice lamellar phases with the correct spacing. So that's exactly what we wanted to see, and in a predictive way, not in a fitted way. We've already fitted things to small molecules, which we're happy with, and that's it. Let me show you another example. This is work what we're still working on, but I think you'll probably find it interesting. We wanted to take this to look at macrocycles, and this is these are some results that were shared by us by Sigurd Høger. These are very nice large liquid crystals which are basically formed like an enormous, if you want to call it like a donut. These large rings are decorated with alkyl chains. But you can decorate the ring in 2 places. You can decorate the ring in one of these corners, and you can see that this tail, or this alkyl tail, has no chance of bending much more than it can bend by its own angles. But if you decorate this molecule here, this benzene ring here, you can see by the nature of the molecule, this benzene ring has full rotation. So this chain can actually rotate and play around. So they're both isomers, but one of them forms a columnar liquid crystal phase. The other one doesn't show any type of liquid phase. And so again, we can do exactly the same type of thing. Recognize, coarse grain it to the level that for example, benzene ring is a sphere, that an alkyl chain is made up of different groups of CH3s form single beads, and just put it all together, producing simple models that would look like this. Again, the greens are the alkyl chains, the purples are the aromatic type rings. In these types of models, we just took two extremes. We put an alkyl chain to the outside and one in the inside. This one in the inside corresponds to the one that could rotate and actually could go in and out, and just to see if we could find things. Remember that one was the one that produced liquid crystals. So again, we do a quenching. We take the molecule which has the alkyl ring tails in the middle, and we quench it, and not surprisingly, of course, we find the columnar phase. I mean, it's a very, I think all of you could have predicted this without too much effort. Right? Let's see if you can predict the next one. What will happen here? You see, again, as we start quenching, we start seeing the appearance of a very interesting lamellar structure. If we take a look at it carefully, what happens is that the rings themselves have segregated from the chains in such a way, and the reason for that is that if we look carefully at the rings, they actually interpenetrate one to each other. So therefore, by interpenetrating, they're decreasing basically their excluded volumes, and therefore they find a more suitable phase. If we look at it, with the order tensors, we actually find that the order tensor is close to -1/2, which is quite strange if you look at the number. But if you think about it a little bit, what you recognize is that there is a director associated with the layering. But as a difference with respect to classical smectic phases and things like that, where the molecules are aligned with respect to the director, here they're actually not aligned. There is actually they have complete rotation around. They're completely disordered with respect to the orientation along these planes. So we found an antinematics phase, which is quite unusual because we hadn't seen anything like that without applying external fields, and we actually got that just by the molecular structure of the molecule itself. So just wrapping up, I just want to go back to the general idea. We have a theory which allows us to bounce back between experiments, between the theoretical descriptions and simulations. And for some situations, simulations will be better than anything else because they can give us insight on things. And for some things, of course, the theory will be the fastest and the most efficient thing, although it has its limitations. For example, this type of theory is useless in terms of describing other things other than isotropic phases. But it does allow us to relate the experiments directly to the simulation by means of this equation of state. I mean, we can always go back from our models. We can go back to the experiments because our beads represent something, and we have very good confidence to what the beads are. I think the most interesting thing is that this is basically a group contribution model. So by filling in that table I showed you with different groups, you can actually use them to build a Lego of different types of molecules and start, doing our simulation games with it. I just want to finish, of course, with saying that, of course, this is not done by me, but as I said, I like that phrase, the royal we. I did nothing; all of these people did all the work. And with that, I'll open to questions. Thank you.
Very nice approach. I was wondering if you ever tried it on thermotropic liquid crystals, and if you think you can be quantitative also on the temperatures, transition temperatures, or concentration for the case of allotropic.
It's very difficult to be quantitative, especially with allotropics. Because as you well know, this is an extremely fine, delicate balance between entropy and energy, and you really have to get them all right. So the boundaries themselves, for example, in the case of the surfactants, we have we have to put a lot of effort to make sure they're right. When we see disagreement and we go back to the numbers and then we recognize that things like, for example, the solubility of one phase and the other was not precisely the correct one, and maybe those parameters were not chosen correctly. For the case of the thermotropic, we haven't done it. But I would think that again, the same thing would happen. That if you wanted to have precise values, you would have to be very, very careful to make sure that your original parameterization was good. Now, the nice thing is that what I showed before was that you have a good prediction in terms of pressures and large temperature ranges, which usually you can't do with other coarse grading techniques. If you do inverse Boltzmann, or if you do other types of coarse grading techniques, you usually are pinpointing one state point, but not necessarily that the parameters for that state point represent the parameters for another distant state point. So representability and transferability are usually the big problems in coarse grading, and we're doing a fudge of all of these conditions to give a general parameter sense.
Peter at the front caught my eye first. I know there are several others in line.
So you're replacing groups of atoms by a single spherical entity, which is my potential. Is it feasible to think about using other blocks, maybe cylinders or some other?
No, for the reason that that at least the way we're looking at it, the parameters for the spheres are taken out of a van der Waalsian type expression. So the equation of state is based on spheres, and spheres putting it to change. But if you want a cylinder, basically what we build is a rigid group of spheres. And that's, for example, the first slides on the T-shaped roll amphiphiles, the white cylinders are rigid. So they form basically essentially a little cylinder made with corrugation. So you could do that, but not directly with a cylinder.
I think Bebo was next.
Claudia.
Claudia.
Yeah, this is very nice for these huge molecules for sure, but if we take even the simple case of CO2, I mean, or in general, you don't seem to treat charges in any way. No, so if you take CO2 and you had a nice PT diagram, but if you go to the solid state, I guess you cannot get the typical architecture of CO2, which is an herringbone without a quadrupole or something like that.
Yeah, well, that's clearly, you're very sharp. That's exactly one of the big limitations is what should we do with charges? For especially if you have condensed phases. So this is work in progress. This is hardly something that is finished. And we actually have people thinking, we have thoughts on this, which I probably will not want to elaborate too much on. But we have
maybe you
recognized this as
could
a
give a
serious
comment
problem.
on this, because you could easily think of adding charges, but then
Yeah,
maybe you are double counting something because you already have something.
No, we wouldn't be doing. I mean, as you say, we could add charges, but then we go back to the same problem we had before. As you say, you're double counting. So we've been thinking more on the lines of looking at some effective potentials that would mimic these charges. And we've had certain successes with ionic liquids, for example, and for which are maybe a little bit simpler.